Hi, my name is Patrick Curran, and along with Dan Bauer, we make up Curran Bauer Analytics. In this episode of Office Hours, I'm going to continue my discussion of the structural equation model. In the first episode, I gave a general introduction. In the second episode, we talked about path analysis. And today I want to talk about factor analysis and introduce the concept of a latent variable. At the end of the prior episode, where I left off is we had built a path model to look at the mediators, potential mediators of parental alcoholism diagnosis on adolescent substance use. And if we think about just part of that model, we had the middle part was stress in the family home leading to negative affect in the adolescent, leading to substance use in the adolescent. All right, these were dependent variables here. We also had covariates, but I'm just going to focus on these three here. And we talked about all the ways that we could build this model, test this model, evaluate mediation. And where I left off at the end of that episode was talking about the assumption the path model makes about manifest variables. So remember, manifest variables are a variable in our data set that we directly observed. So let's say that we had 8 items assessing negative affect. We interview the kid and we have them respond on 8 items about loneliness, social withdrawal, depressed feelings. We add them up and divide by 8 and use that mean score as our mediator in this path model. The path analysis model imposes an assumption that all the variables, we're going to focus on predictor variables, but all the variables in the model are measured without error. So they are perfectly measured. There is no unreliability in the measurements. Well, we know that that is very unlikely when we're studying adolescents, children, most anything, as if we're asking a kid to respond on their depressive symptomatology in the last 30 days, is undoubtedly there's going to be some degree of measurement error in that. What happens if we don't incorporate that into the model, if we assume that it is error-free when there is measurement error in it, is what I talked about in the prior episode, is this regression estimate, beta hat, is on average going to be smaller than its counterpart in the population. It's going to be pushed down. Sometimes the term we have is attenuation due to measurement error, is on average, this regression coefficient is going to be smaller than it should be. And the reason is we're assuming that all the variability that we observed in negative affect is available for modeling, when really that variability is a combination of true score variance with error variance. So how do we address that? Well, within the structural equation model, one of the unique strengths of this approach is we are not restricted to using manifest variables only. We can expand the model to include latent factors. So let's talk a little bit about what I mean by that. Very simply, a latent variable is some representation in our model, some construct that we are interested in, that we did not directly observe, but that we can infer its existence from information that we did observe. What's interesting is you start to think about it is we encounter latent variables in every day. So you have a colleague and you say, oh, well, Mary is happy today. Well, did you directly observe happiness? Not really. What you did is you saw that she was smiling, she was energetic, she was very optimistic, she was very pleasant in her demeanor, and we take that information and say, oh, given all of those behaviors, I think she was happy. Another example, I was walking over to my office just now, and it's a beautiful fall day out here in North Carolina. And so it's a gorgeous day. Well, what does that mean? Well, the leaves are changing color at 70 degrees. There's not a cloud in the sky. There's a light breeze. All of these things, we take in that information and say, I'm going to infer them, this latent construct, that about happiness or depression or self-esteem or any of an infinite number of constructs we might consider. Ken Bolin in 2002 wrote a really wonderful review paper on latent variables. It's in the Annual Review of Psychology, and if you're interested in this, I'd highly recommend it. And he gives a historical review of latent variable analysis and then gives a number of competing definitions. And what he settles on is a parsimonious definition where a latent variable is a variable in our data file that is missing sample realizations, meaning numerical observations, on at least a subset of individuals. Now, typically in measurement models, factor analysis, we're missing observations on everybody. So I'm going to build a model for negative affect, and we didn't observe it on anyone. But Ken has a really nice general definition, because if it's missing on a subset of individuals, then that includes things like missing data or latent class membership or things like that. So we're going to adopt that parsimonious definition of latent variables as one that we did not have a sample realization in our data file. So we do not have a column vector in our spreadsheet that measures depression. We have responses on maybe 8 items that measure depression, and we're going to use those to infer the existence of this underlying latent depression. All right? So what is the point of factor analysis? So there's a huge, it dates back to Spearman over 100 years ago, and where we're left with now is what we want to do is take a set of items that we did observe and make inferences about something that we believe to exist, but we did not directly observe. Okay? So let's say that I asked adolescents in my sample 8 questions about negative affect. So imagine that I come into your home and I give you a survey, and I say, so think back over the last 30 months, how often did you feel hopeless about the future? How often did you feel lonely even when you were in the presence of other people? How often did you feel withdrawn? A number of items. And what I want to do is several things in a factor analytic approach. So the first big one is we want to understand what is the structure, what is the underlying structure that gave rise to these items. So these 8 items, if we use just the letter P to denote number of items, the unique pairing correlations, bivariate correlations between a set of items is P times P minus 1 divided by 2. So if we have 8 items, it's 8 times 7 divided by 2, we have 28 bivariate correlations. All right, so if you had a correlation table that was 8 by 8, there'd be 28 unique correlations within that table. So the first thing is we want to fit a model to understand what gave rise to those correlations. So what's the psychometric structure? Is there one factor that explains all of those correlations? Are there 2 factors? Are there 3 factors? Are there residuals? Those are going to be the leftover variants. Are they correlated with one another? And so one is just assessing the psychometric structure. A second goal that we have is what is very common in any multivariate approach, which is sometimes called data reduction. So we have this very large number of correlations, and we have trouble explaining 28 correlations. Now notice that's only with 8 items. Imagine you had a 20-item inventory, which is not excessive, right? 20 items is a reasonable number. Well, 20 times 19 divided by 2 is 190. So now imagine a correlation table with 190 bivariate correlations and try to make some kind of inference about how they relate with one another. We want to reduce those 190 correlations to a smaller number. So let's say for 20 items, we find there are 4 underlying latent factors. Well, we have 190 correlations, but now we have 4 times 3 divided by 2, 6 correlations among the latent variables that I'll describe more in a moment. And we're able to reduce that dimensionality and better understand the structure of our items and the underlying constructs. And then finally, we could impose structure among the latent variables themselves, so one latent factor predicting another, and that moves us to the structural equation model, and I'll talk more about that in the next episode. So to approach factor analysis, we have 2 main ways we can think about it. I'm only going to briefly talk about the first one and then more about the second. The first is called exploratory factor analysis. And what that is we're going to turn to the characteristics of the data, and we're going to let the data speak to us about how many factors are needed to adequately reproduce the correlations that we observed. All right, so Remember, if you saw it in the prior episode, I talk about path diagrams, and a square represented a variable that we measured. So these are the items, they're in our data file. The single-headed arrow like this is a residual variance. And so in an exploratory factor analysis, what we're going to do is say, well, I've got these 8 items, and I don't know how many factors are going to explain these. So I'm going to select a number of them, and then using certain rather subjective criteria, I'm going to determine what is best. So what we might do is extract one latent factor. All right, it's circle, representing that we believe it exists, but we didn't directly observe it. And that is going to have an impact on all the items. All right, so maybe we would denote this eta 1. All right, that's a Greek symbol we'll use in the SEM, eta, ETA, eta 1. These are factor loadings. All right, they're sometimes called lambdas. All right, each of these have a lambda. All right, and these are the residual variances. Sometimes we'll call these epsilons. All right, and then the variance of the epsilon we'll refer to as sigma squared. All right, so this latent variable, at least in the EFA, we don't usually do mean structure in the EFA, so it's only correlations or variances and covariances. It will have some variance that I'll denote by a double-headed arrow, and we'll call that psi. So here, we have a single latent factor that impacts all 8 items. These are the factor loadings, lambda. And in the EFA, what we'll do is say, well, I'm going to extract one factor, and then I'm going to extract a second factor and see if that improves the fit, a third factor. There are entire textbooks written about how do you determine the optimal number of factors. There are things called scree plots that are visual. There's Kaiser-Gutman rules. There are all sorts of things. We don't have time to talk about that. That's a whole nother issue. But we extract one factor, and that's going to partially explain the bivariate correlations among the items. Then we can say, well, does a second factor explain the remaining residuals among the correlations? So it's going to go back through. Now notice what it does though in the EFA is all items load on all factors. So notice now we have eta 2. So that is also going to have a variance. We'll call psi 2 and we'll call this psi 1. And if we do rotation, it's called an oblique rotation. It allows a correlation between the two. And what this says is we have these 8 items, and they're explained by 2 latent factors. So in EFA, totally data-driven, is we don't know how many factors there are a priori. We let the data speak to us. We decide how many factors we determine are optimal. Is it 1 or 2 or 3? And we have to justify that. Then we do a thing called rotation, factor rotation, that I'm not going to talk about now, but what that does is rescales the factor loadings so that they are more interpretable, and there are dozens and dozens of options for factor rotation. And then we have interpretation, and we say, okay, well, it turns out maybe that these 4 items load really strongly on factor 1, so I'm going to put these in green, really strongly on factor 1, but small 5, 6, and 7, and 8 have small loadings, but 5, 6, 7, and 8 have large loadings on factor 2, but small loadings with, 5, 6, 7, 8. Those 4 items have strong loadings with factor 2, but 1 through 4 have small loadings, weak loadings. And what we might do is then look at the item content and say, oh, the first 4 were more like depressive symptomatology kinds of questions, and the second 4 were more like anxiety. And so we're going to name the first factor depression, and we're going to name the second factor anxiety. And so then we would go on there with our analyses, as maybe we would use these to get scores for other analyses, maybe we would use these results to better refine our measurements. So if we went out and collected a new sample, maybe we would change the wording or add items, whole lot of things we could do with it. So this is very powerful. It's very cool. I mean, if you ever have a chance to learn more about it, I find factor analysis almost magical as you take these massive correlation matrices, extract the factors, estimate the loadings, and then using equations I'm not showing you here, you imply what the correlation structure should be, and then for a good fitting model, that correlation structure is very close to what you did observe. There's almost a magical component I find that is very, very cool. But what's the big limitation here for a lot of work that we might do? And the big limitation is there's no theory in this. There are no a priori hypotheses. There are no restrictions placed on the model. We're not making any statement about how our variables relate to one another. We're utterly letting the data guide us. Now that is fine in a lot of applications, and I'm actually a big supporter of that, as I think it can be used in really exciting and interesting ways, but it is not a priori. We're not testing a theory. So that's exploratory factor analysis. Well, how do we remedy that? Well, let's pull this off. One thing I want you to remember from this path diagram is that all items loaded on all factors. All right, so item 1 through 8 was on the first factor, and item 8, 1 through 8 loaded on the second factor. Remember, those factor loadings were the one-headed arrows connecting the circle to the square, okay? And what we're going to do now is we're going to move to what's called a confirmatory factor analysis. A lot of parallels, as you would imagine, with the exploratory factor, but it's very, very different in a lot of important ways. What we're going to do is, as the name implies, with confirmatory factor analysis, or CFA, is we're going to hypothesize a particular number of latent variables. We're going to hypothesize how the latent variables are associated with the observed items, and then we're going to test that with respect to the data that we observed. And the closer that our factor model, our hypothesized model, corresponds to the characteristics of the data that we observed in our sample, the better fit we have. And so the closer we believe that our hypothesized model is to some population generating model. So let's say going into it that we know the first items are assessing more about depressive symptomatology, and we know that the second 4 items are assessing more anxiety, anxious symptomatology. So what we're going to do is not just extract as many factors as we think are needed, but a priori, we're going to say, all right, I observed these 8 items, I observed these 28 correlations, and I think they can be explained by 2 latent factors. I'm going to call it eta 1, and I'm going to call it eta 1 and number it 2. It's going to be eta 1, this is eta 2. I believe them to correlate with one another. They each are going to have variance. Notice the similarity. It's exactly the same so far of what we saw in the EFA, but here's the huge difference. I'm going to say eta 1 is responsible, gave rise to, is causally related. Use the word cause here because we have a single-headed arrow, but use it very cautiously, right? Because we can only talk about consistent with cause, and it's a design issue to make a stronger inference about cause. But we are saying that the correlations we observed among our first 4 indicators are due to eta 1. But notice what I'm going to do with eta 2. I'm going to say eta 2 gave rise to the second 4 items, but eta 1 is not related to 5, 6, 7, 8, and eta 2 is not related to 1, 2, 3, or 4. I have imposed restrictions. I have taken parameters out of the model. I said eta 1 does not predict 5, or 6, or 7, or 8. I've imposed 4 restrictions, and vice versa. I've imposed 4 different restrictions, coming back the other way. And this is why it's sometimes called a restricted factor analysis, or more commonly, confirmatory factor analysis. And so this is how we would initially set up a 2-factor 8-indicator latent variable model. Okay. Now, there are many steps in doing this that I'm not going to detail here, just given scope and time. This step is called the specification. So how do you specify your model? How do you link what you observed to what you did not observe? Do we believe them to be correlated? Does this have a covariance or not? Are there cross-loadings? A cross-loading is an item that is defined by two factors or more than two factors. Are there correlated residuals? This is the part of the item that we observed that is not associated with the underlying latent factor. Maybe part of that relates to one another. That's the specification. Now we have to move into what's called model identification, and that is a very complicated topic. We have some heuristic rules that we can use. And if you remember, if you happen to watch an earlier video, identification is do we have enough information observed in our sample to uniquely estimate the parameters that we're interested in? And there are many ways of going about doing it. And I'm not going to talk about those here, but this model is identified. So we have more information that we observed in our sample than what we're going to estimate in the fitted model. All right, so that's going to be the identification. And then we have a unique step that is an endless source of confusion in applied work, but probably shouldn't be because it's kind of an isomorphic issue. That is, there are two ways that we can do it that are exactly equal. Is we did not directly observe eta 1 and eta 2, right? We believe it to exist. This is depression, this is anxiety. We believe it to exist, but we didn't directly observe it. We can infer its existence as a function of the information that we did observe, but we have to set the metric of the latent variable or the scale of it. That is, where's the location? What's the dispersion? Is it, from a kind of colloquially, is it in inches or feet? What is 0? What does a 1 unit represent? And because we didn't directly observe it and have to establish this, we can do this using one of two ways. Where you'll sometimes see is that we will estimate the factor loadings. All right, remember these are again called lambdas, and the variance of the latent factor we will fix to 1.0. All right, we're going to standardize the factor. So the variance and thus the standard deviation of the latent variable is going to be 1, and we'll standardize this, we'll fix that to 1, and we will estimate the factor loadings in this way. All right, that's one way of setting the scale. The second way that is numerically exactly the same is we're going to estimate the variance of the latent factor, just as we did before, but we're going to set the factor loading for one of the items to 1.0. Often software packages will automatically just pick the first item. It's actually generally it's inconsequential as to whether you pick the first or second. There's some minor deviations from that, but we can just pick the first one and set the scale. And what this is going to do is it's going to put the latent factor in the scale of the first item. And we could work through some covariance algebra to show that, but notice the symmetry. We either estimate this and fix this to 1, or we estimate this and fix this to 1. They're numerically equivalent. And there's some advantages and disadvantages in different applications as to which of these you would use, but it really doesn't matter. Most software packages for CFA will automatically fix the loading to 1 and freely estimate the variance. And also notice, because of, again, just time in these videos, it would take hours to talk about these in detail. These models can be estimated with mean structure, but we're not doing that here because we're not imposing means on the model. It's actually kind of funny, excuse the dinging, is I got a text message and it's Bauer, so he's telling me something. I will look at it when we're done here. So we've set the scale. Now we would estimate the model. All right, so we fit it to the data. We get back our fit statistics. A later episode of Office Hours talks about how we do model fit, chi-square fit indices, things like this. But we follow exactly the techniques that we did in path analysis. That is, do we have adequate model fit? If we do, can we cautiously move forward in interpreting the parameters? But if it doesn't fit, what do? Well, as I talked about in an earlier episode, we can use likelihood ratio tests to introduce parameters from an a priori fashion. So do we believe residuals to be correlated? Do we believe there to be a third factor that we didn't hypothesize? Or we can again use modification indices to say, well, the model would be substantially improved if we allowed these two residual variances to correlate with one another. All right. Now, sometimes those you want to avoid. Those are easy ways of making a model fit better. They're not strongly related to theory, but there are other times that you could look at the items and maybe you have two items that are worded in a similar way. So maybe, 1 and 2 is assessing depressive symptomatology at home and 3 and 4 at school. And you can make an argument that there's a little mini home factor and a little mini school factor. We might want to introduce those to account for that. But be careful in how you use those correlated residuals. Sometimes that's kind of a cheap way of getting your model to fit better. Now, to stress, I use those, and I have in the past. I'm not being pejorative about them, but be careful in their use. So what have we done over the EFA? We have drawn on theory. We have specified a model in an a priori way. We are over-identified, so we're able to make statements about model fit with respect to the characteristics of the data that we observed, and now we can make some evaluation about the utility of the model. And so we have some sense of psychometric structure, we have some sense of how the items are related to one another. So where might we go from here? Well, there are two ways that we could proceed, and one is we could potentially use this model to obtain scale scores. So instead of just adding up the 4 items and dividing by 4, we could get what's called a factor score estimate. Any software package will give you this, but it will draw on this model to give you an estimate of this that might be eta hat 1 and an estimate of this that might be eta hat 2. And we could use those in subsequent analyses. But that's always not the best way to go about doing it. Is if we can, what we would like to do is retain the latent factors in later analyses, if that's where we're proceeding in our research application. So if we got these eta hat 1 and eta hat 2 and took it to a path model, we're still back in the situation where it's assuming perfect measurement reliability. Now, in a lot of cases, these are better than just taking the mean of the 4, but they're still not error-free. So what we might like to do, the second option, is to say, all right, let's expand the model to maybe we want to include predictors. Remember, we had age and gender and parental alcoholism diagnosis, so maybe we want to have some covariates that predict the latent factors. Maybe we want one factor to predict another factor. Maybe we have a third factor that's some distal outcome, and we want to test mediation of a covariate through eta 1 to eta 2 to eta 3. All of those fall under the general structural equation model. And so what a structural equation model is, as we'll see in the next episode, is a logical combination of what we talked about for path analysis with this in the latent variable and the confirmatory factor analysis. Is we're going to estimate the factors and then do all the interesting things that we can do with them in the path analytic framework, but bring those two traditions together. And that'll be the topic of the next episode. So I hope you found this of some use, and Dan and I really appreciate your time